Hello, this is Valerie Mueller again, trying to review the important material covered from Chapter 9. And Chapter 9 dealt with the role of sampling in inferential statistics. There were several important topics covered. We want to be able to basically use statistics computed from a sample to draw conclusions about unknown parameters in the population. And why do we want to be able to do this? Because most agencies cannot fund data collection for the entire population. So instead, they survey a simple random sample of the population and then try to infer from the statistics characteristics about the general population. In order to be able to do this, we need to establish some underlying properties of the distribution of these characteristics. And that's where describing the sampling distributions of means empirically and theoretically are particularly handy, especially the central limit theorem. So the central limit theorem basically states that given a population of values that is of no specified distribution, with mean equal to mu and standard deviation sigma, the sampling distribution of means for sufficiently large samples drawn randomly with replacement from this population has a shape that is approximately normal, a mean equal to mu, and a standard deviation, also called its standard error, equal to sigma over the square root of n. And n here is the sample size. So just to give you a sense of how useful applying the central limit theorem is, I'm going to go over an example, but I also assigned several questions for you to do in your study guide. So the example is, suppose we're given a normally distributed population of 5,000, and that population has scores with mean equal to 15 and standard deviation equal to 3. So first we want to know what will the corresponding sampling distribution of means for samples of size n equals 16 with replacement look like. And then we would like to know, if we were to select a single sample of size n equals 16 at random from this population of scores, what is the probability that the mean for the sample will fall between 13 and 17? So for part A, it's straightforward. Because the parent population is normally distributed, we know from the central limit theorem that the sampling distribution of means also will be normally distributed, and that its mean will be equal to 15, the mean of the population, and that its standard deviation will be equal to the standard deviation divided by the square root of n, which in this case is 3/4 or 0.75. What about part B? Part B requires again to use the table 1 that we were using for solving the problems in the previous chapter. Because we're making a statement about the sampling distribution of means, which is known to be normally distributed with mean 15 and standard deviation 0.75, we can go ahead and use this table. So to find the area between 13 and 17, we first have to convert those into z-scores, and I went ahead and solved those to be negative 0.267 and 2.67. So if you use the table, you can see that the area to the right of 2.67 is 0.0038. And we know that the normal distribution is symmetric, so that the area to the left of negative 2.67 will also be 0.0038. So then to find the area between 13 and 17, we simply take 1 minus 0.0038 minus 0.0038 and get 0.99. This indicates that almost all such sample means fall within the specified range. Anyways, I think I assigned you several problems so that you can go ahead and play with this yourself. Please make sure to do the problems, only because your mini exams will draw from those. So if you have all the answers handy, then you're sure to get 100% on your quizzes. Anyway, good luck, and again, don't hesitate to contact me on Canvas. Take care.